last time we were talking about these inverse functions, and we made the following observation, that we saw an example where when I found the inverse, it was a function. Another example where I found the inverse, and it wasn't a function, right? You guys remember that? And the question we were kind of left with was, can I tell when it's going to be a function, when it wouldn't be? That's where we're going to pick up from today. But before I start doing that, I should probably give you guys a chance to ask questions from like homeworks and stuffs. So put a pin in that for just a moment, because that's where we're going. But let me answer some questions first, because that's the right thing to do. Zoe?
How do you do like 29?
29 or 30? Sure. I guess I'm going to need that other page now, huh? Oh, okay. So it says find two functions f and g such that the h of x given is the composition of the two functions. So when I'm looking at one of these, I'm basically looking for like an inner function and an outer function. So if I'm looking at 29, sine looks like my inner function.
Oh, okay.
And x squared minus 1 would be is my inner, and sine is my outer. So f of x, you might just make sine x. That's the outer. And g of x, you might make x squared minus 1. And that could be your inner. That's the kind of the obvious thing to do. Is that the only answer? No. You could have done f of x is equal to sine x minus 1. And then g of x could just be x squared. Right? That would be okay. When I compose those, I still get h. Or there's the ultimate cheat code, where f of x could just be the whole thing, and g of x could just be x. Or vice versa, you could make f of x x and g of x the whole thing. So any of those would be, those are probably the four most common answers for that, but this is probably what I was kind of expecting, is something like that. Just look for an inner and an outer. But there's lots of possible answers. Does that feel cool? Yeah. Chanel.
Number 27.
27 says using the results from question 5, find g or f compose g of 5. Okay. So f compose g of 5, well, f compose g of x from that one would have been square root of x minus 4, right? That's what you got for 25?
Yes.
So f compose g of 5 would just be the square root of 5 minus 4. Square root of 1, so on. That's all. Or you could have thought about it as, also, you could have done f compose g of 5 is f of g of 5. So you could go back to g. If you plug 5 in, you'd have 5 minus 4, which is just f of 1. And then when you plug 1 in, it was the square root of 1. So you could have done it that way also. Either's fine. You get 1 either way, though. Happy? Cool. Who's next? I saw some other hands, didn't I, or no? No, I didn't? That's okay. Oh, yeah, hold on. Ariana.
Yeah. Is the homework quiz only 10 questions?
10 questions is bonkers length. It's like going to be like 3 questions.
Oh. Okay.
And again, the way I'm grading these things is I'm just kind of looking at overall, I'm just kind of looking holistically. So like it's on a 10-point scale, but I'm basically going as the work you've given me, like A work, B work, C work, because if you get one wrong and there's 3 questions, what's that, a D? Like that's bonkers. Like Mr. Kula can't do that, right? So it's going to be a little bit more holistic.
Okay.
Like if you do basically everything right and you just make some like silly mistake or 2, that's probably like a 9 or a 10. You know what I mean? So even if you're getting like multiple questions wrong, if it's for like simple stuff like, oh, you miscopied the question or something silly like that, you still can get full points for something like that. You know what I mean? And on the other end, say you get everything wrong, like as long as you have like a clue what you're doing, you probably can get a 7 or an 8. Like it's, that middle is pretty beefy. So it's like hard to do really bad. Pretty easy to land somewhere in that 8 range. It's pretty easy. You don't have to be able to do a lot. You know what I mean? Because I'm not giving you much in terms of like what to expect and really always even when to expect. At this time, we've been a little bit more specific about what to expect. But in general, I would tell you if like, you know what stuff means and you've done the homework up to the, through, 22 or 24 or something like that, you should feel fine. Should be like, okay, I remember doing this. And maybe I don't remember exactly what to do, but if I have like the right ideas, I can probably get an 8 or a 9 still, even if it's just like, I think it is what I do. Like this stuff we've done, I'm not like just making stuff up. You know what I mean? So like, don't get freaked out. And plus, it's 10%, right? It's the smallest category. So even though it has the Q word attached to it, your homework is 2.5 times, or worth 2.5 times more points than the homework quiz. Probably spend 2.5 more times doing homework than you would preparing for a homework quiz. So like, why flip those? Why flip the percentages? You know what I mean, guys? Yeah. Anyways, cool, Ariana.
Yeah.
Does that help at all? Okay. Yeah, 10 questions is like that's a lot of stuff. All right. Yeah. So, everybody cool? Should we go? Let's hit it then. What did I do here? Oh, I see what I did. No, I don't see what I did. That's what I did. I did something like that. Close enough, whatever. Nobody cares. All right, back to where we were, right? We saw that sometimes when we take an invert or find the inverse of a function, sometimes we get a function, sometimes we don't. We'd like to predict when that inverse will be a function just by using what we know about f, right? I don't want to go through all the hassle of finding the inverse if it's just going to be like some gobbledygook that's not a function. That's usually not that helpful to me. All right. So I'm going to hit you with a series of definitions here, and we're going to put them all together, and we'll get something. So we say that a function is considered onto or some textbooks use the term surjective. If every element in the range is mapped to by some element in the domain. Is mapped to, I got to stop reading and writing at the same time. Do you guys remember talking about this term in your Algebra 2 class? Did you talk about onto? If you didn't, that's okay. I don't remember. I think I do when I talk about when I do the Algebra 2 class, but that's, again, having taught like all of these things like a million times, you know, like, oh, I can squeeze this in right now, and then it's, at least you've heard it once before kind of thing. All right. We say that a function is considered one-to-one, or the term that is sometimes used is injective, if every element in the domain maps uniquely to distinct elements in the range. And then we say that a function that is one-to-one and onto is bijective. And that was the term that we needed. So we can say that a function is bijective if and only if f inverse is a function. So note that that's an if and only if statement, so it reads both forwards and backwards. So that a f inverse will be a function if f is bijective. Oops, a function f. So let's take a minute and kind of walk through some examples of what it really looks like when one of these things, like for a function that's onto versus not onto, or one-to-one versus not one-to-one, and why those are necessary conditions to ensuring that f inverse will be a function, right? Because it's probably not obvious from the definition why we need these properties. Cool with that? So I'm just going to kind of go off to the side. So I'm just going to use a mapping diagram because it's usually the easiest to kind of see what's going on. So here's an example of a function that's not onto. You can see that it's not onto because we have some element in the range that is not mapped to. Everybody's okay with that? If I then construct f inverse, the domain of f I get from the range, the domain of f inverse comes from the range of f. And the range of f comes from the domain of f inverse. No, and the domain of f inverse comes from the range of f. Great googly moogly, Mr. Kulik. What do you notice about f inverse here? Yeah, well, it's not a function, right? Because not every thing in the domain goes somewhere, right? So what onto, if a function is onto, it guarantees us that its inverse will not have any unpaired domains, right? That's what onto is going to guarantee for us, is it eliminates the possibility of having an unpaired domain in the inverse. Everybody's okay with that? All right. Let's do another example here. Oops. I like the thick pen. So here we notice that this function f is not one-to-one because one of the things in the range is mapped to by more than one domain, right? The domains aren't mapped uniquely to distinct ranges. So here we have two domains going to the same range. That makes that function not one-to-one. If we then create the inverse, what do we notice? That inverse is not a function, right? Because we have one domain going to two ranges. So if my function is one-to-one, that guarantees that the inverse can't send one domain to more than one range. So if I take those together, one-to-one and onto, that'll guarantee that my inverse, every domain gets used from the onto, and each of those domains go one place from one-to-one. That is the definition of my function, of a function, right? So take those two properties together on f, guarantees that f inverse will be a function. Without those, you might not be a function, which is what we saw in the last example from last time, that function f is not one-to-one because one of the y coordinates is used more than once. And when we found our function, we had an x coordinate, or found our inverse, we had an x coordinate that was used more than once. Does everybody kind of understand what we mean by one-to-one and onto? Why they're good, why we can use them to predict when f inverse will be a function? Now, pretty easy to see this when I give you guys a mapping diagram. How often do we give you a function as a mapping diagram to work with, though? Almost never, right? This is just kind of like to do the conceptual piece. Almost never is it's like, here's a mapping diagram, you know, blah, 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 blah. It's like, you're almost never going to do that. So let's talk about what these properties look like, one-to-one and onto, in some of the more common representations, namely a graph or an equation. Okay? Which one of these two do you think Mr. Kulik's going to talk about mostly?
What?
Well, no, graph or equation. That's okay. I would say graph. Why? It's really easy to go from an equation to a graph, right? Everybody agree with that? Is it easy to go from graph back to an equation? No, that's often quite difficult, right? In some cases, like seriously difficult. Is everybody cool? So mostly we're just going to talk about what one-to-one and onto looks like when we have a graph. Okay? Because it's easy to take any equation, turn it into a graph, and just look at your graph. The calculator will do it for us, right? Okay. So, remind me, when I have just like some arbitrary function, how do we calculate its range? Well, it's really the possible outputs from the domain, right? Is what the range is. It's all the possible outputs that you get from the domains, the allowable domains. What does that mean about every single function we talk about that's represented as an equation or a graph? They're all onto. If we're assuming the range is just the stuff that can output from the function, then everything in the range comes from something, right? So everything is going to be onto. So that's not the part we ever have to worry about. Oh, swell, right? By the way that we're calculating ranges, we automatically have onto. Oh, neat. I wasn't expecting that, Mr. Kulik. So really all we have to worry about is one-to-one. What is one-to-one going to look like? Something that's not one-to-one has a repeated y value. So is this one-to-one? No, because, for example, this y value we can see is used more than once. Does this look familiar? What's this look like? What does this remind you of? Looks like the vertical line test, except in this time we're drawing a horizontal line. So this is a horizontal line test. What this does is it checks if f is one-to-one, and that is equivalent to checking if f inverse is a function. So they do that is equivalent statement if we have a function that's defined as an equation or as a graph, that's good enough. Do you guys feel okay with that? Very easy, right? I can do it in just a second. All I need to do is look at the picture of the graph, and I can immediately see whether that function's inverse will be a function. All I have to do is do a horizontal line test. Awesome, right? Hugely helpful. Okay. Let's talk now about finding inverses. We've done some examples of finding an inverse when we did a mapping diagram, right? That was easy. You just switch the domain and range sets and reverse the arrows. Everybody's cool with that? Do we need to do another example on that? We've done a bunch of them along the way here the last day or two. Okay. If we have a function defined as a set of ordered pairs, think we did this last time, right? We did an example of this last time. Was that easy? Yeah, what did we do to get F inverse? Just swap the x and y coordinates, right? The math term for that is called transpose. You transpose the x and y coordinates. Ooh, fancy. What we haven't talked yet about is graph and then equation, right? So let's do an example with a graph, and then we'll do some examples with the equation, because that's the one that gets a little bit more varied, and I think is the one that's maybe a little bit trickier. All right, so let's say we have this function here. I'll call it y equals f of x. And I want to draw the graph of the inverse. Typically, when we ask you to find the inverse of a function, we want it in the same form that the function was given in, right? So if I give you a graph, the inverse you give me back should be a graph. If I give you an equation, the inverse you should give me back should be an equation. You know, like, that makes sense, right? So what do I do with this? Well, I would start. Notice I'm given 3 coordinates. What do you think I'm going to do with those? Switch the x and y's and plot them, right? So 2, 5, I'm going to plot as like 5, 2. 1, negative 1, I'm going to plot as negative 1, 1. And then 0, negative 3, I'm going to plot as, wow, what did I do here? Look at this. That's not 2, 5, Mr. Gulick. That's negative 2, 5, you dof. Well, you know what, guys? Sometimes we just have a bad day every once in a while. Great googly moogly. All right, that's better. And then negative 3, 0. Everybody's okay with that? What I just plotted? Okay. Actually, this is not quite in the right place. Okay. All right. Anyways, so how do I connect these? What's going to be the key? Yeah, so this point was the vertex in F. What point should be the vertex in F inverse? This one. Is everybody okay there? Did you notice anything about the symmetry going on here? Didn't do a great job when I drew this. Oh boy, that was really bad. If I look at this line y equals x, it looks like these two graphs are reflections of each other across that line. Not a coincidence. Now, I didn't do a very good job because realistically, this point and this point should have been on that green line. but we do the best we can without having to like grid the thing out. I guess I could pick the graph paper background. How do I do that again? Does anybody remember? Is it view? Yeah. Could have done that. That would have made it life easier. We'll do it next time. Does that, you guys get the idea though? Not a big deal. It's pretty straightforward what you're doing. Yep.
Okay.
Yep. A graph is a valid representation of a function, right? What do we notice about this F inverse in this case? It's not a function, right? And that shouldn't be a surprise because F was not one-to-one. Everybody's cool? Okay. Let's do some equation ones. We'll do a whole mess of these. Because it's a great refresher on some algebra skills from last year. So first things first. What kind of function do I have here? Linear function. Very good. Is a linear function one-to-one? Definitely, right? It's line, or just like a straight line. That definitely passes a horizontal line test. So I would expect F inverse to be a function as well. Cool? All right. The way we're going to do this, I'm just going to replace the f of x with a y equals. And then I'm going to use algebra to get the x by itself. So to do that, what do I have to do? Add 7. And then divide by 3. Everybody's cool there? And then we swap the x and y variables. So that should be my, oh my goodness. Mr. Kulik, what are we doing here? I don't know. It's the end of the day. There's my inverse. Is everybody cool there? Chanel?
I just have a question with the graph. So would the like inverse now be a function with like horizontal?
Well, so in the previous example, the inverse was not a function because f does not pass a horizontal line test.
Oh.
Right? F inverse would fail a vertical line test because it's not a function. But that's not, we would have used f before we constructed the inverse to determine that. Does that, so it's like, it depends on what we're talking about, right? Which one goes to which.
Yes.
Okay. Is there a way for me to check this to make sure I've done this correctly? What do I have to do? I do the composition both ways. Right? I do my composition. The times 3 and divides by 3 cancel. And then the plus 7 and minus 7 cancel. So that one looks pretty good. What do you guys think? Cool? Again, you don't have to check these unless you're directed to. But if you're like, I wonder if I did that right. There's your check. All right. We ready for this to start getting tricky? All right. How about this one here? Ew, boy. This is a simple rational function. You should recall that from last year. A simple rational function will definitely pass the horizontal line test, as it just looks like two hyperbolas separated by a horizontal asymptote. Everybody agree? Or at least now that I say it, you're like, okay, if you say so, that sounds familiar. So function, or the inverse should definitely be a function. I'll start by changing h of x to a y. We're trying to get the x by itself. What do I have to do here? That's a great idea. So let's multiply both sides by 5x minus 8. First thing I'd want to do is get rid of the pesky old fractions there. And let's go ahead and distribute that y through now, because why would I want that parenthesis hanging around? Okay. What now? These were great ideas. Well, that's going to just put you back to what we had the step before if I factor y out. I would put the x's all on one side, right? I have a 5xy on one side, so I'm going to subtract that 2x over, and then I'll just add that 8y to the other side. So I have only the x pieces on the left. Everybody's cool with that? Now what's the problem here? I have x in two places, right? How can I put x into one place with what I have written here? Factor. Good. What kind of factoring am I going to do here? Just like a greatest common factor, right? The simplest kind of factoring, like pre-algebra factor. Everybody's cool? And then I can divide both sides by 5y minus 2. Oops, I didn't call this F, I called it H. I don't know why I called it H, probably because my notes had it as H. Everybody feel okay there? This trick, where we factor out the negative, or factor out the x to get into one place, will come up again. Will come up in the homework. It's a good one to remember. Whenever you have x in more than one place, and you're finding one of these inverses, you're going to have to do some factoring. Okie doke. Let's just check this because, again, the algebra here is a little bit tricky and wouldn't be a bad idea to review that. So here I'm plugging in this, right? So I'm going to have 2 times this fraction plus 5 divided by 5 times this fraction minus 8. Oh, Mr. Kulik, this looks like yuckarooskies. Do you remember what this kind of object is called that you're looking at right here, where you have fractions inside of a fraction? This is called a complex fraction. Potentially you talked about that last year in your Algebra 2 course. Does that phrase ring a bell? Some of us saying yes, that's good. So what I'm going to do to simplify this complex fraction is I'm going to multiply the numerator and denominator by the same thing to clear the small fractions out. What should I pick there? That thing that I'm going to multiply the numerator and denominator by is going to be the least common multiple of all denominators. In this case, my only denominators are 5x minus 2 and 1. So the least common multiple is just going to be 5x minus 2. Everybody's okay there? When I multiply it to this term, the 5x minus 2's cancel to leave this. When I multiply to this term, I get that. Is everybody okay? And then I'll do the same thing down here. So what do I have here? 16x plus 10 plus 5x minus 10. And I'll have 40x plus 25 minus 40x plus 16. So when I do that, I have 21x on top and oh no, what happened here? It's not right. Plus 25x. Oh, yeah. Thank you. That's what's wrong. I swear I can do arithmetic, just maybe not necessarily at teaching hour like 7 for the day. You know what I mean, guys? You've been there. You're at the end of your day also. Thank you for pointing that out. Everybody's cool? We still have another direction to do. I'm not going to actually do that because algebraically it's like the exact same steps. Are you guys cool with just skipping that? Because it's just going to take a long time and it's not going to add any other insight that you would have gotten here. This step was the one that was the super helpful one in seeing what to do with that, getting the complex fraction out of there, right? Okay. Let's look at another. I guess I'm calling this one P of x. I don't know what I was doing when I was writing these notes. Ruh-roh, Raggy. What do you notice about this function, p of x? It's a parabola, right? That's a quadratic function. Its graph is a parabola. Is that one-to-one? No. What do I notice about, what can I say then about p inverse? I don't expect this to be a function. Can I still do this? Yeah. But because it's not a function, what am I going to expect to see in here? Probably a plus or minus at some point, right? I think in section 1's homework, we saw that oftentimes if you had got the y by itself and you end up with a plus or minus, you weren't getting a function. All right, so we'll add 4 to both sides, divide both sides by 3, square root both sides. So there's my yucky non-function p of x. Do you guys remember doing that? Now, do you remember what we did in Algebra 2 to take something like 3x squared minus 4 and alter it a little bit so its function would be an inverse? What we did there, we did something called restricting the domain. So if I look at the graph of 3x squared minus 4, that's a parabola. And the problem is I have all of these repeated y values in it, right? So I'm going to just pick to restrict my domain so that I'm only using 1/2 of my parabola. Doesn't matter which half I want to restrict it to. Everybody's okay with that? So my choice is I'm going to restrict my domain to just be the x's that are greater than or equal to 0. Everybody's okay with that? So when I do that, and I get to this step where I have x is equal to plus or minus the square root of yada, 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 what can I say if x is to be greater than or equal to 0? I can't have the negative, and I end up with a inverse that's a function now because the plus or minus drops out of there. Okay with that? So if you see something where it's like you have that additional piece at the end, what that additional piece on the end is a restriction to the domain to ensure that your inverse is a function. What you have to be careful about is when you get to the x separated by itself step, you use that restricted domain to decide whether you want the plus or the minus, right? If we had chosen to take everything less than or equal to 0, then we would have taken the minus sign there. So it's not just like, oh, I don't have to worry about the plus or minus. It's having to choose, depending on how you restricted the domain, which one you'd want. Typically, the convention is to restrict the domain so that you dump the minus, but that's just the convention, right? Because obviously, like, if I can pick between something with an extra negative sign or something without the extra negative sign, which one would I rather have? The one without the extra negative, right? If I'm free to choose, that's the one I would pick, but there's no reason you have to do it that way. You know what I mean? All right. Let's do a couple more. We're back to F again, somehow. Okay. What type of function is this? Square root function, right? What's the graph of a square root function look like? Just kind of looks like that, right? So that passes horizontal line test, so I have no problems. So replace it with a y, get the x by itself, so we'll square both sides. And then subtract 5 and divide by 12. And there's my inverse. One thing to keep in mind here, the domain here is the x's that are greater than negative 5 over 12. Everybody's okay with that? And the range here then would be 0 to positive infinity. So this range is going to become the domain for this quadratic, because you don't get the full quadratic. You just get 1/2 of it. Do you know what I mean? Here, let's look at the picture real quick. So there's my absolute value function. Here's the line y equals x. When I reflect across that line, I'm just going to be getting part of this guy turn those axes off real quick. So here's f, here's y equals x, here's the inverse. So the inverse is really only giving us like here to here, right? You know what I mean? I shouldn't have all this other stuff. Do you guys understand? It's okay to say yes or okay to say no if you don't. Yeah? Okay. Okay then. Okay then. E. What type of function is G? Where is the x located? In the exponent, so it's a exponential function. Great. So, what's an exponential function look like? Just a hyperbola that passes a horizontal line test, nothing to worry about here. So, rewriting this with a y. What's the first thing I have to do to get that x by itself? I'd get rid of the 1/2, negative 1/2 out front. So multiply both sides by -2. We good there? How do I get the x out of the exponent up there? A log. Very good. So if I had my choice of any log will work, but which log would be the easiest one to choose? Log base 3. Very good. Why log base 3? Because it matches the base of the exponential. Everybody's remember that? So this is what we're talking about, is that log base 3 will cancel exponent base 3 directly. If you had picked another log to use, that's okay, but like you're going to have some leftovers. It's not going to just cross out all willy-nilly. And I'd much rather just pick the nice log and cross things out willy-nilly than use like any, just like the same log every time and be stuck with all the leftovers. You know what I mean? And so the last thing I do is divide by 4. I'm just going to write it as times 1/4 though, so that I don't get confused about whether that is supposed to be inside my logarithm or outside my logarithm. You guys okay with the 1/4? Do you want to check this one just so we can see the logs and exponents kind of interacting again? That's probably worth doing, right? This is a good algebra reviews. Yes? And we're just going to go one direction also. Like, well, this one might be a good one to do both directions, actually. The algebra is not awful. Okay, so there's the composition. Yikes! Is everybody okay with how I compose those two things? And I just took that and stuck it in place of the x for f. So I noticed the 4 and times 4 can cancel each other out. Or 1/4 and 4, excuse me. And exponent base 3 and log base 3 will cancel each other out. And in doing so, that's going to bring the -2x out of the exponent. Just leave us with x. Does that look familiar from your log studies last year? If it doesn't, that's okay. It'll come back. The key is remembering that log base b cancels exponent base b, and vice versa, that exponent base b cancels log base b. Tessa. So these two canceling each other out leaves the -2x out of the exponent. Like the same reason why the same thing happened here, right? Does that? Okay. Let's go the other direction though also because, well, it's good algebra review, if nothing else. And this was basically just Algebra 2 review that we've been doing this chapter, so let's do it, you know? I'm excited. Are you excited? Yeah. I've been less excited, Mr. Kulik. Well, I guess that's fair enough. Bunch of negative Nancys in here. I'm just joking. But not really. Everybody's okay here. Again, this is what I'm plugging into F inverse. So let's see, -2 and -1/2 cancel each other out. Log base 3 and exponent base 3 cancel each other out. That leaves just the 4x, no longer in an exponent, and that reduces down to x. Does that feel okay? Coming back a little bit after you're seeing some, like, how does this canceling work again? Excellent. All right. I don't even remember what letter am I on. What letter am I on? F? Yes. F is for finished. Back to H, I guess, according to what I'm reading. I don't know why I'm at H again. All right. What type of function is this?
Does that say log?
It says ln. What is ln again? Natural log, which is the same as log base e. Very good, Christian. Log base e. What type of function do we have? It's got a log in it, so it's logarithmic. What does the graph of a logarithmic function look like? Just whoop, kind of like that. Does it pass horizontal line test? Yeah, that's the point. So we're good. Nothing to worry about here as far as domains go. So let's get that x by itself. First thing I should do is multiply by 3/5 to get that log part by itself. And then how do I cancel out the natural log? I think somebody mumbled it, but I couldn't hear because it was kind of quiet. E, exponent base E. So this is the way I always try to draw it. It's cool, like that's an enormous E. Why are you writing it so big? Well, I want to make sure that when I look at my notes, I don't accidentally think I'm multiplying by E, because I'm not. I'm using the exponent base of E, and, like taking E to the left-hand side equals E to the right-hand side of my equation, right? Everybody's cool? All right. Just like before, exponent base B cancels log base B. Now that I've done that one step, I'm going to be less psycho with the size of my exponent base. And then I can just add 1 and divide by 7, right? Does that feel okay? Yeah, should be all right. Let's do the check, though. Again, the algebra here is good review. Do we actually have to do the check when we find the inverse? Not unless we're asked for it in the directions. This is just reviews, you know? It's all review, guys. I know. We'll get to the new stuff here soon. I have one more section in this chapter that we're supposed to do. And it's kind of a bear of a section. It's all the transformation stuff. Oops. Everybody's good with the composition? What do I cancel first? Sevens. Very good. After that, what can cancel? Nope. Not the e's and the logs. Got to dump those plus ones and minus ones out of there. Then the log e's and the exponent can go bye-bye. How's that feel? It's all right? This all kind of jogging some memories. Maybe not good ones. Logs were usually hard. No, not bad? Good. At least for some of us, right? I saw some head shakings. Horizontal shaking, I guess. Not vertical shaking. Vertical shaking would be yes. That was hard. And I guess it's okay if it was. It's not like we're going to see logs all over the place. I just put them in here so we can review stuff. You know. Then we do the other way. So we're going to have e to the 5/3 times, 3/5. It's like that's not right. Then 5/3, natural log 7x minus 1. Plus 1 over 7. Oh, there we go. Sorry, I had missed a closed parenthesis there. There we go. All right. 3/5 times 5/3 gives me e to the natural log 7x minus 1. Still have my plus 1, still over 7. E's and natural logs cancel out. So I have 7x minus 1 plus 1 over 7. Plus 1 minus 1 go bye-bye. 7x over 7 is just x. How do you guys feel? Does this all seem a little bit more familiar? Kind of jogged your memories doing this kind of stuff? You probably didn't find inverses for things with logs in them last year, but you certainly solved for logs last year. And is this process really any different than a solving process for a log? And it's basically the same thing, right? To find the inverse and to solve a log, just you have a y there instead of a number, but the algebra is the same. So let's see, that finished out section 7. So you guys should be able to do now up through 56. So where did we leave off last time? At 30, right? Where's that going to go